Okay, everyone, it is a couple minutes after 11, so we're going to go ahead and get started. For those of you that don't know me, my name is TC Beinke, and I'm the National Account Manager for the Testing Division here at J.A. King. So today we're going to talk about solar testing. And to get started, I just want to define what solar testing actually is. And it is the exposure of a specimen to either natural or artificial illumination, which approximates natural sunlight. And there's a few different reasons that we perform this kind of testing, but essentially it's to simulate stress on a material caused by a solar load. And you can see I've included some examples here for some damage that we see caused by solar loads. Up in the top left-hand corner, you can see a steering wheel that's obviously gone through some cracking and embrittlement that's been caused by the sun. Another thing that we see quite often is color fade. So if you look in the bottom left corner, you can see a good example of sun that's come through the window and caused some color fade on those hardwood floors. And we also see some display errors sometimes on outdoor displays, such as displays on gas pumps or outdoor televisions. So if you look up in the top right-hand corner, you can see an example of some errors occurring on that display. And then also, oftentimes you'll get warpage from a solar load. So if you look down at the bottom right-hand corner, there's a picture of some warpage on siding that's been caused by sun exposure. So there are a few different types of solar testing. Mainly we've got natural exposure, fluorescent UV, Xenon Arc, infrared, and then full spectrum solar simulation. And these all focus on basically the same concept, but they're going to utilize different types of equipment, and then also different types of tests oftentimes are going to focus on different portions of the solar spectrum. So to break down that spectrum, here is a diagram of the solar spectrum. And we can see at the low end, we've got UVC radiation. And this is mostly used for sterilization. And UVC radiation is actually filtered out by our atmosphere. So it's going to fall outside of the range of most solar simulation systems. And typically, if you do UVC testing, you're really just using that for sterilization. So there's actually specific specialized equipment that's used that outputs just that UVC radiation. Now, if you move up in the spectrum a bit, we hit UVA and UVB. And these are typically the main cause of both part deterioration and also color fade. And then if you move further up in the spectrum, we've got visible light, which is typically the secondary cause of those same factors as well, both part deterioration and color fade. But it is important to note that different materials and different pigments are going to be affected differently by different portions of the spectrum. So while you've got some pigments that might experience a lot of color fade down at 300 nanometers, you're going to have other pigments that experience color fade more from that visible light portion, maybe up in the 500 nanometer range. So a lot of solar simulation equipment is going to try and focus on a relatively wide spectrum. And then if you move up in the spectrum even more, we reach the infrared light portion, and this is what's going to contribute most of the heating effects of solar radiation. So the first type of solar testing I want to talk about is natural exposure. And this is essentially what it sounds like. It's actually taking parts or test plaques and actually placing them outside and letting them be exposed to true sunlight. So obviously this type of testing is very realistic, and it's also inexpensive because you really don't need much equipment. If you look down that picture I've provided at the bottom, that's the setup for most natural exposure tests. You've really just got your test parts or plaques and then very simple fixturing. But there's some downsides to natural exposure testing too. One of which is it's uncontrollable. So you're really not going to be able to control parameters such as temperature, humidity, and irradiance. Obviously, you can control them somewhat by choosing where you're going to place these parts, what kind of geographic location you're going to put them in. But day to day, those parameters really aren't completely controllable. And also, natural exposure testing is quite slow. So if you want to simulate 10 years of solar exposure, you really have to take parts and sit them outside and let them stay outside for 10 full years. So oftentimes people are going to opt for more accelerated testing And we'll talk about those methods here in a minute. And I also wanted to point out that specifications typically focus on either dry or humid climates because that moisture content is going to affect the test results a bit. So typically specs either focus on testing in the Kalahari Desert for dry testing or in Florida for humid testing. So the next type of testing I want to talk about is fluorescent UV. This is a form of accelerated testing, but it focuses on a relatively narrow wavelength. It's going to focus on the 300 to 400 nanometer range. And this is based on the concept that most damage is going to occur from those shortwave UV rays in that 300 to 400 range. So it's only going to focus on damage that is going to be caused by those radiation wavelengths. But also fluorescent UV testing is controllable. So you can control parameters like your irradiance, which is really just your light intensity, and then your temperature and humidity as well. And the next type of testing I want to talk about is Xenon Arc testing. Unlike fluorescent UV, this is going to focus on the entire solar spectrum. So not just UV, but also visible light and also infrared radiation. And the spectrum can actually be altered a little bit by using different types of filters. So some of the most common filters are daylight and window glass filters. And daylight filters are going to simulate true sun exposure, whereas window glass filters are going to simulate sun coming through window glass. And this is especially useful for color change and light fastness testing, mostly just because it does output that wide wavelength spectrum. And similar to fluorescent UV testing, this is controllable as well. So you can control your irradiance, your temperature, and then typically Xenon Arc testers either can control relative humidity or they'll have a water spray function to introduce that moisture. And you can see a picture of a Xenon Arc tester there on the right. This is a tray style tester. So for this setup, you're going to have a light bank up top, and then your rack of specimens is going to be below that. Another setup you might see, which is also a Xenon Arc chamber, has a bit of a different configuration where there's a vertical column of light bulbs, and then you've got specimens that actually rotate around that light source. And the purpose of this is just to make sure that all the specimens receive a uniform irradiance. So the way that we do that with the tray style tester is just by periodically changing the location of your test plaques. So I talked a bit about the different types of filters. And this is an example of a plot of their actual output. So this is plots of daylight filters. So if you look at the black line, that's going to be your actual direct sunlight. And then the other lines are just different types of daylight filters. And the reason that you might choose one filter over another might depend on your actual specification. Oftentimes that will require a specific type of filter or what region of the spectrum is of most interest to you. So for instance, if you look at the lower end of the spectrum between about 300 and 400 nanometers, you can see that red light, which is a daylight F filter, most closely approximates true daylight. So if that's the part of the spectrum that you're interested in most, that might be the filter that you choose. And then this is that same plot, but just with window glass filters instead. Again, you can see that black line is actual sunlight through window glass, and then the other lines are different types of filters. Again, you might choose the filter based on the specification, or with window glass filters, you might also choose which filter to use based on what type of glass your parts are actually going to be behind when they're in the field. And the next type of testing I want to talk about is infrared testing. So this is only going to focus on the infrared portion of the spectrum. So because of that, when we're doing infrared testing, we're focusing mainly on heating effects and specifically directional heating. So this is going to be different than, for instance, just performing heat aging testing on parts, because with radiation, you've got a directional heating component. So this is also going to be especially useful for checking for warpage, so expansion and contraction of parts. And then also an infrared tester, typically, including the ones that we have in our lab, can be placed inside an actual climate chamber too. So you can control your ambient temperature and humidity, and then also have a radiant heat source. And the next type of testing that I want to talk about is full spectrum solar simulation using metal halide bulbs. So similar to Xenon Arc testing, this is going to focus on the entire solar spectrum, so UV, visible, and also infrared. We also have control of parameters for this type of testing, so you can control your temperature, irradiance, and your relative humidity. And as you can see from that picture, with full spectrum solar simulation, you're actually in a true climate chamber. So you're going to have a lot more room for test parts. You can pull a lot larger parts in here. And also your control parameters such as temperature and humidity are going to be a lot wider. So you can actually hit a lot more extreme temperatures such as extreme lows and extreme highs, and you're going to have a little bit more control over relative humidity as well. So oftentimes for full spectrum solar analysis, we are testing automotive interior components. And in that case, we will usually use solar boxes. And these solar boxes are going to be used to simulate actual vehicle interior conditions. And the way it does that is by allowing the greenhouse effect to take place. So I'm sure you're all familiar with if you take your car and park it outside and leave it there for a while, you're going to have a temperature inside the vehicle that's going to be much higher than the ambient temperature outside. And that's because you're going to have this radiation coming in through the windshield and through your side windows, and some of that heat is going to be trapped inside the vehicle. So that temperature is going to increase quite a bit. So by using solar boxes, we can get that same kind of effect. We can have a higher temperature inside the solar boxes than is actually the ambient temperature in the chamber itself. And when we create these solar boxes, there's a few different parameters that we have to keep in mind and that we have to control. Some of them being airflow velocity. And the way that we can control that is by the actual geometry of the solar box itself, and then also by utilizing air holes. So if you look at the diagram on the right, this is a basic diagram of a solar box. And you can see I've pointed out multiple air holes at the bottom of that solar box. And so those can be plugged or opened up to help regulate the airflow velocity. Also, window composition is going to be important. You want to use the same composition that's in the actual vehicle. And we also perform what's referred to as temperature layering. So if you look at all those different locations I've pointed out in the diagram, those are the different locations that we take temperature measurements. So we'll actually place thermocouples in these various locations to make sure that we get the correct type of temperature layering that we look for. We also are looking at relative humidity and then also the windshield angle. And the windshield angle is actually going to have effect on some of these other parameters, such as mostly your temperature, and it can affect your relative humidity a bit as well too. And typically these parameters are all going to be defined in either your test specification, or they're going to be, you're going to want to match them to the actual vehicle that you're testing. And this is just an example of an image of a solar box that we created here at J.A. King. It is somewhat configurable. We've got holes in the side of the box that can be plugged or opened up. And then also the windshield angle can be changed based on the actual parts that we're testing. So next I want to talk about the actual effect on test parts caused from solar testing. And there's really two main types of effects. You've got actinic effects and your heating effects. Actinic effects are basically chemical effects caused by radiation. And the most common type of actinic effects are both color fade and then deterioration and loss of strength. So for color fade, this is tested best by using some sort of full spectrum solar exposure, whether it be metal halide or Xenon Arc. And typically to evaluate this, we're going to take measurements using a spectrophotometer or a grayscale, and we're going to take measurements both before and after testing to evaluate if there was any color fade. And then deterioration or loss of strength. This is caused because there's actual photochemical reactions that take place during solar testing that can break down the bonds of both polymers and elastomers. And again, we want to make sure we can accurately evaluate this too. And the way we do that is by material testing, such as tensile testing, compression, bending, or flexural modulus testing. And the next type of effect that we might see on parts is heating effects. So solar radiation is going to provide a different type of heating than heat aging, similar to the infrared radiation testing that we talked about, it's going to have directional heating. So you're going to have different parts that are going to heat up at a different rate and to a different temperature than other components of your part. And this is going to depend somewhat on the actual material properties. The different materials are going to have different absorbance and reflectance properties. So that's going to affect their heating during testing. And because of this, you're going to have components that might expand and contract at different rates. So this is going to potentially cause a lot of stresses at component interfaces. And ultimately, all of this can lead to warpage. And the way that we like to check warpage is by using a photogrammetry system. And these are some images of an output of photogrammetry. Basically, the way this works is we take snapshots of your parts both before testing and after testing, and then overlay those images. And you can see this is the output we get. It's essentially different displacement vectors giving you an easy way to see how your part's deformed. So in this case, you can see we've got our total displacement up in the top left-hand corner, and then we also break that down to X, Y, and Z, all the three orthogonal axes. So when you do decide to go forward with solar testing, there's a few different parameters you're going to have to consider. You're going to have to think about your irradiance, or the actual intensity of your solar load, your temperature, relative humidity, the duration of the test itself, and then part orientation too. So this can refer to the angle at which your part is fixtured, because that's going to affect which face of your part is going to receive the direct radiation versus which parts receive the indirect radiation. And then whether or not your parts need to be shielded behind glass or maybe even put into a solar box. And when you're choosing these parameters, there's a few different factors that could influence these. One of which being your geographic location. So where are the parts actually going to be used? What latitude are they going to be used at? Are they going to be used in a humid climate, or are they going to be used in an arid climate? Things like that. And then also your time of day that the parts are going to be used. So if they're going to be used mostly around noon, they're going to receive noonday sun exposure, which is going to be primarily vertical, and it's going to be relative high intensity. Or if they're going to be used towards dawn or dusk, they're going to receive horizon sun. So that's going to be a lower intensity, and of course, it's going to be coming in at a different angle as well. So one of the most difficult things oftentimes to decide on is your irradiance. So one easy way to choose this is by using an irradiance map. These can be found online, and you can see this is just color-coded based on light intensity. And as you can see here, the closer you get to the equator, the higher that irradiance level is. So I just want to now go through an example of designing an actual test and walking through the steps and choosing all of these parameters. So in this case, we're going to assume that we're testing an automotive interior component. So the first thing that we're going to want to look at is irradiance. Usually when you're designing a test, you're always going to want to base it on the worst case scenario. So if we're looking at irradiance, 1050 watts per meter squared is noonday sun at the equator. So that's going to be your worst case scenario. So that's what we're going to go ahead and choose for this test. And then for temperature, if you've got an automotive interior component, it's going to be used in multiple climates where you're going to see a lot of temperature extremes. So we're going to choose a pretty wide temperature range of negative 30 degrees Celsius all the way up to 45 degrees Celsius. The next thing you want to going to want to look at is relative humidity. So again, it's an automotive component. It's going to be used in different climates. So what we can do in this case is split up the test between dry days and humid days. Dry days being at 30% relative humidity and your humid days being at 70%. This way we kind of cover all of our bases. And then duration, this can be another tricky one to define because unfortunately there's no universal acceleration factor for solar testing. So typically what you have to do is take some field data and use that to determine an appropriate duration by correlating the effects you see in your field data versus what you see during testing. So for this case, we're going to go ahead and say that we're going to test for 18 days, which for automotive components is actually quite standard to simulate 10 years of in-field usage. And then for part orientation, we're going to want to fixture these parts in car position. And because they are automotive interior components, we're going to use the solar box as well. So now I want to talk a little bit about measurement and monitoring equipment. So the first piece of equipment we're going to talk about is a pyranometer, and this is used to measure your irradiance, essentially, or your hemispherical solar radiation flux density in watts per meter squared. The reason that we use a pyranometer is because it can measure a very wide wavelength spectrum. So we already talked about the spectrum of solar irradiance, and it's quite wide. So we want to use a piece of equipment that can pick up all of that radiation. And pyranometers can be used both to collect field data. So if, for instance, you don't want to use those irradiance maps or you want something a little bit more accurate, you can actually take a pyranometer, set it outside where your parts are going to be used, and collect some field data. And you can also use a pyranometer during the actual test itself to help monitor the test and make sure you're hitting the values that you want to hit. And when you're using a pyranometer, there's a few guidelines that you want to stick to. One of which is that your horizontal plane, or the actual height that the pyranometer is set at, is crucial. So you're going to want to make sure that the height your pyranometer is at is the same height as the height of your parts. Because if your pyranometer is closer to the light source, you're going to have higher values. If it's further away, you're going to see lower values. So you want to make sure that height matches that of your part. And then also the angle of orientation is crucial. If you've got parts that are flat, facing directly those solar lights, you want your pyranometer to be flat as well. If it's on an angle a bit, you're going to affect those values as well. And the next piece of equipment I want to talk about is a black panel thermometer. And this is used to measure your surface temperature during solar testing. It's a little bit different than just a standard thermocouple because, as you can see from the picture, it's got a black coating on it. And this is used to absorb different wavelengths of radiation. So essentially what this is going to do is act as a black body during testing. So it's going to provide an estimate of your maximum possible surface temperature during testing. And again, just like a pyranometer, this can be used to collect field data to help you choose your parameters of testing. And it can also be used to monitor the test as well. So next I want to talk about some of the common specifications that we run into for solar testing. For true full spectrum solar simulation using those metal halide lamps that we talked about, there's a couple that we run into, one of which being DIN 75220. This specification is geared mostly towards automotive components, both exterior and interior components. And for interior, it actually does specify the use of the solar boxes as well. And then MIL standard 810G, for those of you that aren't familiar with this test standard, it covers a lot of different types of testing other than just solar. But for most of the tests in this MIL standard, including solar testing, it provides really more of guidelines for testing, but you're going to have to tailor the test a bit based on the needs of your parts. And then for Xenon Arc and Fluorescent UV, we've got ASTM G154 and G155. As you might guess from the numbers, they're very similar test specifications. One is just geared more towards fluorescent UV equipment, and the other is geared more towards Xenon Arc. But for both of these specifications, there's multiple different cycles in there, so you're going to have to choose which cycle makes sense for your parts, and then you're also going to have to pick a duration. And then, of course, as with most types of testing, there's tons of OEM specifications out there as well, and oftentimes those specs will actually reference back to one of these other specs that I've already mentioned. So next, I want to talk about some customer testing that we did for our customer Peerless AV. They make audio and video components, as well as outdoor displays. And outdoor displays is what we were testing when they came here to our facility. And what we did here, you can see an image of the test setup on the right. We actually used mirrors in this case to redirect the light radiation to a horizontal radiation direction instead of vertical. And the reason we did that is we wanted to actually keep the displays vertical so that we could maintain proper orientation for gravitational effects, since that's the orientation that the parts are actually going to be in during field use. And during testing, we had multiple thermocouples that were placed on both the interior and the exterior of the part. And then we also had video cameras that were set up throughout testing so that we could check for any display errors. So this is a good example of how we can take a general test specification and then modify it to create a custom test based on the needs of the part. So during this testing, you're able to use some extreme conditions to provide data to the customer to aid them in product development. And the product performance was evaluated to quantify the robustness of the displays to make sure they could actually hold up to all those environments when they were used in the field. And then they actually did find some areas of improvement in their product design process. And one thing that they were evaluating as well was the product cooling during these extreme conditions. So finally, I just want to talk about some of our capabilities here at J.A. King at our Greenville, South Carolina lab. We have Xenon Arc testing, and you can see the tray size there. For Xenon Arc, we can go from room temperature all the way up to 90 degrees Celsius. And our specific Xenon Arc chamber has a water spray function. For full spectrum solar simulation using metal halide bulbs, they're much larger chambers. Both are 16 by 9 with 10 feet tall ceilings. And you can see the temperature range is quite a bit wider as well. We can go all the way down to negative 65 degrees Celsius up to 177. And then those both have relative humidity control. And then we do also have infrared radiators as well. We've got 2 infrared radiators on stands. Both are 3,000 watts. And they're mounted on a stand on wheels so that we can adjust the position however we need to. And then the radiators can actually be placed inside a climate chamber as well so that we can control the ambient conditions of the test. And that is all I have for you guys today. Do we have any questions?
I actually do have a few here.
Okay.
Someone wants to know if you can use the solar boxes for things other than automotive parts, such as items that would be visible in your home through a window or something of that nature.
Yes, definitely. So solar boxes can be used for more than just automotive interior components. Really anything that's going to be used behind any sort of glass, we can create a solar box for. And like I talked about in deciding the parameters of these solar boxes, the way we would do that is just take some field data, figure out the correct angle of orientation, temperature, humidity, and we would use all that data to create a solar box.
Are there any other filters other than daylight and window filters?
Yes, so daylight and window glass filters are definitely going to be the most common that you run into, but there are some different filters if your specifications require that. So one of probably the third most common is an extended UV filter, and that's actually going to include a portion of that UVC part of the spectrum. And the reason that's usually used is to help accelerate degradation of parts.
And how can you accelerate a test?
Okay, so there's a few different ways to accelerate testing. We can choose our temperatures to help us accelerate testing, so we can increase the high end and decrease the low end a bit. You can also increase your irradiance. So when I was going through designing a test, we chose an irradiance of 1,050 watts per meter squared. This is going to be the irradiance at noonday irradiance at the equator. So this is a worst case scenario, so that can help you accelerate testing. And then also the duration of time that these parts are exposed per day. Typically for automotive testing, we'll expose parts to that noonday irradiance for 16 and a half hours a day, which of course is much longer period of time than they'll actually get exposed to per day in the field. So this can help you accelerate testing as well.